In the previous video, I have introduced you to the concept of exciton and organic materials that can act as an electron donor and an electron acceptor. Let's make a solar cell using organic materials. Since doping is not preferred in organic materials, by intelligently using intrinsic materials, we can initiate charge separation in an exciton. Using the concept we just discussed in the previous video, we can theorize that by bringing together an electron donor and an electron acceptor, the interface formed will resemble that of a heterojunction. The lack of doping, however, results in the absence of a depletion layer, since the width of the depletion layer is inversely proportional to the doping levels, which in turn removes any electric field formed by a depletion layer. Thus, this heterojunction will lack any sort of band bending, as can be seen in this figure. However, while bringing together these electron donors and electron acceptors by aligning their vacuum levels, we bring about a misalignment in the HUMO and LUMO levels. This produces an electrostatic force at the interface, which can be very useful for our purpose of charge separation. An exciton formed by the excitation of an atom can be split at this interface if the electrostatic force is high enough. Hence, indirectly, the interface formed acts like a p-n junction that separates charges. The effective band gap in such a heterojunction interface becomes the difference in energy levels between the LUMO of the electron and the HOMO of the electron donor. In a normal heterojunction organic solar cell, the organic absorber material exhibits a high absorption coefficient and hence requires an absorber layer with a thickness of anything more than just 100 nanometers to maximize the utilization of the solar spectrum. On the other hand, the inherent nature of the excitons to recombine easily gives a diffusion length of around 20 nanometers. The total thickness of the solar cell must however be limited by its diffusion length, which in this case is much shorter than what is required for a satisfactory absorption of the incident light. The probability of absorption of light in the region beyond 20 nanometer from the interface, leading to effective charge carrier separation at the interface, is very low, which hence results in a very low quantum yield, as can be seen in the small animation. To overcome this barrier, a bulk heterojunction solar cell is used where the electron donor and acceptor material form a sort of blend instead of two distinct, well-defined layers as before. This reduces the path length of an exciton in meeting a donor-acceptor interface, thereby reducing the probability of recombination and increasing the quantum yield of the solar cell. The split electrons travel through the acceptor layers and then into the metal electrode, while the holes move through the donor material and get collected at the front ITO electrode in this example. The conventional cell architecture of organic molecule and polymer solar cells is based on blended heterojunction solar cells. The donor and acceptor materials are blended in the absorber layers. This allows the excitons to reach a donor-acceptor interface before they recombine. The separated electrons travel through the acceptor layers and are collected at the electron collecting layers, abbreviated here with ECL, while the holes move through the donor material and are collected at the hole collecting layers, here abbreviated with HCl. Typical organic solar cells have two cell configurations. The first configuration is called the regular configuration, which means that the whole collecting layer is first processed on the glass ITO substrate. The inverted structure is when the electron collecting layer is processed first on top of the glass ITO substrate. So, the electrons have to be collected at the window side where the light is entering the cell. The holes are collected at the backside. A large variety of organic acceptor donor blends have been developed in the last 20 years, and it's out of the scope of this lecture to mention all blend combination. As a typical electron collecting layer, zinc oxide or titanium oxide have been used in many organic device concepts. PEDOT-PSS, molybdenum oxide, tungsten oxide are often used as hole collecting layers. To further improve the conversion efficiency, the logical route of organic multi-junction PV devices has been explored. Over the last decade, progress has been made in terms of development of new photovoltaic organic materials. Many low bandgap and high bandgap materials have been discovered and processed. In addition, many tunnel recombination junctions and buffer layers have been developed as well. Too many to mention here. Here the typical regular and inverted solar cell configurations of the tandem organic photovoltaic cells are illustrated. Here you see an example of a tandem cell in a regular architecture. An organic material blend with a low bandgap material is used in combination with a blend with a high bandgap. Here we see an example of an inverted triple junction device. The bandgap of the organic PV blend is tuned from high bandgap for the top cell, medium gap for the middle cell, and low bandgap for the bottom cell. In addition, the corresponding band diagram of the triple junction is shown. The electron generated in the bottom cell recombines with the hole generated in the middle cell at the recombination junction formed by the PEDOT-PSS and the zinc oxide. This is the same for the electron generated in the middle cell and recombines with the hole generated in the top cell at the second recombination junction formed again by the PEDOT-PSS and zinc oxide. Here an example of an organic PV module product available on the market is shown. It is the Helia Sol module, which is lightweight and a flexible module that is produced by the German company Helia Tech. As discussed earlier, the lightweight and flexible nature of thin film modules allows many new PV applications and integrations in comparison to glass encapsulated modules. In this video lecture, you have been introduced to organic photovoltaic technologies. We have discussed the fundamental principles of organic semiconductor materials, like how does carrier transport occur in organic molecules. You have been introduced to the concept of excitons, its generation, the diffusion of excitons, and charge separation through heterojunction. In addition, the typical architecture of bulk heterojunction and organic solar cells have been introduced as well. Currently, various multi-junction concepts are under development for the organic PV technology. In the next video, we will discuss another PV technology that is based on a relatively new kid on the block, the perovskite materials. So, see you in the next video.